Alright, in this video we're going to talk about domain and range. So we're going to start looking at some real-world applications, or real-life applications. The area of a circle depends on its radius. So the function notation would be a of r equals r squared. What's the independent variable? Remember, in function notation, your input is always the part that's inside the parentheses. So that tells me that my independent variable is the r, which means the radius. So let's think about that. The radius of a circle. It's got to be greater than 0, doesn't it? I might even say greater than or equal to 0. Okay. The dependent variable would be the area. It's depending on the radius. That's area. Resulting values of the dependent variable. Well, if you stick in values of radiuses that are greater than or equal to 0, that means we're only going to get out values that are greater than or equal to 0. This next one, the length of a box is twice the width. Thus, it depends on the width. So the width is the independent, length is the dependent. Well, width of a box needs to be greater than 0, and, well, so does the length. The next one talks about state tax on food. It's 5%, and the amount of tax you pay depends on the cost of the food you bought. Well, the cost of the food is what is independent. The tax depends on that. The cost has to be greater than 0. That means our tax has to be greater than 0 because you can't have negative money. Now, in this set, this isn't really a real-world set. We just have a set of ordered pairs. In this case, since it is very distinct, discrete data, just points, then we're only looking at those points. Now, our independent variable is again the S, it's displayed there, and the dependent is the D. The S values that make up the domain of this, which, that domain is your independent variables, is 1, 2, 3, -1, -2, -3. Nothing else. So I would use roster notation for that. And usually we like to write them from smallest to biggest, just because that's proper. For our range, which is our set of dependent values, it's 1, 4, and 9. So again, the domain are allowable values of the independent variable. Now let's see if we can write each of these domains in interval notation. Now our first one I put as r is greater than or equal to 0. I could have made an argument that it was just greater than 0, but I'll go with what I have. If it's greater than or equal to 0, that means our domain starts at 0 and goes to infinity. Why did we restrict it? Well, radius is a length, and lengths can't be negative. And I'm not going to do the rest of them because I think you can get that idea. The range are the resulting values of the dependent variable. And again, they couldn't be negative. And then on our last one, it was just distinct points. So of course it's restricted to only those values. Now, on the graphs is where I've seen most of the people having trouble. So let's make sure we go over this very carefully. On each of these graphs, it's x's and y's. So our independent variable is always the x. Dependent is always the y. We're going to assume that when they go off the picture, that they keep going on and on forever. And this is just the pointer of saying where that graph is at that time, and it's at the point 0, 4. My domain, or what are the x values that have points associated with them. Well, since this keeps going on and on forever this way and this way, all of the x values have a point on the graph associated with them. So it's all of them. Now the range, none of these y values have part of the graph associated with them. It doesn't start till we get till 4, and then it keeps going up to infinity. So the range on this one is 4 to infinity. This next one, this one's a little weird. This graph keeps going on forever this way and this way, but look what's happening right around our axes. It gets close and it shoots off this way, and the same thing here. I want you to really think about that for a second. This function is the function 1 divided by x, 1 over x. When x is 0, can we even get an answer? 1 divided by 0 it's undefined. We can't do it. So we're okay with everything else on the left side and everything else on the right side, but it just can't be 0. Now to do that in interval notation, we'd say negative infinity to 0, not including 0. That gives me that side of the graph. This side of the graph starts back over at 0 and goes to positive infinity. And they are unioned. The next, oh wait, we forgot the range. Since it's doing the same thing on the range, well then our range is going to be the same. Now, let's look at number 7. Do you see how the graph starts here, goes up, and then goes down here, and it keeps going forever? So technically, all of the x values going this way along the x-axis will have points on the graph associated with them, but nothing on the left side. So my domain starts at 0 and goes off to infinity. Now my range values, do you see how I have an upper boundary here? That's at the point when y is 5. Now do I have a lower boundary? Some people might think it's here, that that's the lower boundary. But look, that arrow means that that part of the graph keeps going down and down and down and down. So there is not a lower boundary. The range starts at negative infinity and goes up to 5 and stops. Number 8, domain and range. Again, since this is going to the edge, we assume that it keeps going off and off forever. So on this one, there is no break or anything. The domain would be all real numbers, or negative infinity to infinity. The range, do you notice that we have a lower boundary here? And luckily, the cursor is actually at that point. And that point is 2, negative 8. So that's telling me that my smallest y value is negative 8. And it keeps going up from there, so it goes off to infinity. Number 9 starts here and stops here. There's nothing else to the graph. So that is negative 3 to 3, including both of them. The range is from here to here. So that would be 0 to 3. And that's it. Alright. This keeps going on forever. Goes up to here. And then there is a break. Starts back over here and goes off the other way. So we have 2 pieces to that graph. And let's think about this on the x-axis, and sometimes this may help you. We start down here, and we're going up to here, and we're going to include that point. Then we're going to start back over here and keep going this way. Those are the y values we want to write down. Starts at negative infinity, goes up to negative 1, and there's a break. We start back up at 2 and go to positive infinity. Now for the range, I have a lower boundary. It's down here, And then it just keeps going up and up and up and up. So what's the lower boundary? -1, -2. It's -3. So the range is -3 to infinity. The next part of this assignment talks about the domain of functions based on their equations, the domain and range. So what we want to think about is, are there any values of x that are not allowed? So if we look at the first one, 3x plus 1, there are any values of x that are not allowed? No, it's a line. So our domain there would be -infinity. Oh, we want set notation this time. Oops. So that's not, I was going to do interval notation. This one would be x is an element of all real numbers. We use the curly brackets. And why is it restricted? It's not. So what's the range of a line? Oh gosh, well that's the same thing. But here make sure you put y's where y is an element of the reals. And it's not restricted either. The next one, f of x equals 1 over x. We kind of talked about that on the graph. When you have a fraction, the only thing that can't happen is the denominator cannot be 0. So the denominator cannot be 0. So in this, we want all x's except x cannot be 0. Now, let's think about what we got out of it. If you remember the graph over there, the y's were not 0 either. And that's because the only way in division to get 0 as an answer is if the numerator is 0. Since the numerator is 1, we can't have 0 as an answer for the y values. Now let's look at this next one, square root of x. Is there anything that you can't take the square root of and get a real answer? Yes. Can't take the square root of a negative. So that means that x has to be greater than 0. It's okay to take the square root of 0. It's okay to take the square root of 1, 2, 3, 4, just not the negative numbers. Now, what's nice is that my y's, oops, greater than or equal to 0, I forgot, you can't have 0. Your y's will also be positive because the coefficient there is 1, which is positive. The next one, 1 over 2x minus 6. Again, we have a fraction. The denominator cannot be 0. So what would make 2x minus 6 equal 0? Well, the value that you could plug in that would make that be 0 is 3. So we do not want x to be 3. Again, since 1 is in the numerator, y will never equal 0. X minus 2 underneath the radical. I again want x minus 2 to be greater than or equal to 0. So that means that my x's have to be greater than or equal to 2. No negatives under square roots. Now, this one has a negative in front of the square root. That means that all of my answers will be negative or 0 because the coefficient is negative. So the big two types of domain restrictions, denominator cannot be 0. Big one. So thou shalt not. And here, can't take the square root of a negative. You do get an answer, but it's not a real number answer, so that's why we're having to restrict it.